Howdy, students. Thanks for joining me. I really appreciate you sending me lots of questions this week. That was great. Let's keep it up. I will try to make this short and sweet, but address sort of as many of those things that came up as I could. I think the best one of those is to just work through an example problem that came up on the homework. So, you probably had a problem that was somewhat similar to this. And it says that given this function by the graph f of x, that we're supposed to estimate the integral from 0 to 10 of f of x dx with 5 subintervals using, and then it wants us to do all three, left endpoints, midpoints, and right endpoints. So the first thing is to notice we want to go from 0 to 10. So that's 1, or 0 here, 10's here. And we want to do it with 5 subintervals. So if we do that, then each interval is going to be, well, this is length 10. Dividing that by 5 gives us 2. So our intervals are going to be splitting it up by 2's. That way. Okay. And then in order to do, say, left endpoints, use some color here. So we'll call our left endpoints orange. So then all I do is find in the box, I go to the left side of it and draw a box that's even from the x-axis up to that. So then the next interval, left endpoint, is here. So that box goes across there. The next left endpoint is here, so that box is just 0 because the left endpoint is 0. This left endpoint is -2 supposedly. And this one is here. Okay, so then I can now calculate the area of all these boxes. This one has height 3, and so its area is 2 times 3, that's 6. This one has height 1 times 2, but it's below the x-axis, so it gets signed area, so that's -2. And this box is 0. This box has -4. 2 by 2, and it's below the x-axis. This one is 2 by 2, but it's above the x-axis. If we add those up, we get 4 minus 4 is 0, 6 minus 2 is 4. So our answer for that left endpoints would be 4. Okay, let's do it again with midpoints. These will color green. Okay, so midpoint of this one, 0. Midpoint of this one, -1. Midpoint of this one, also -1. So that's, just to make it clear where my green boxes are. Midpoint of that one, 0. Midpoint of this one, 3. So that includes all of that. Okay, so notice some of our boxes might have overlapped, but 0, this is 2, 4, 4 plus, this one has 3 times 2 is 6. So 4 plus 6 gives us 10. Okay, last time, right endpoints. We'll color these purple. So I just find my interval, find the right endpoint. Purple, that one's -2. Right endpoint, 0. Right endpoint, -2. Right endpoint, +2. So even though this one has sum to below, I just ignore that because I'm just going by the right endpoint here. Right endpoint 4. Adding up the purple, -2 minus 4 is -6, plus 4 gives me -2, plus 8 gives me 6. Hope I did that right. So that's what we have to do. Remember, if it's above the x-axis, it's got positive area. If it's below the x-axis, it gets negative area. The reason for that is because most of the time we don't actually care about area. If this was, say, describing the velocity of a car, then this is when it's going forward, and this would be when it's going backwards. So if it goes forwards a certain amount, this much area, and then it goes backwards the same amount, we want to say that those are, well, the car is back at the same spot. So it went 0 total distance. So therefore we have to say going forward and going backwards are opposite signs. That happens all the time. My bank account, I know when I'm spending money and when I'm making money, so I can add those two together or subtract the numbers apart. Take making money, subtract spending money, and then I would have money flow. I don't care if I'm, say making money part of the year and spending money part of the year, if at the end of the year I come back and hopefully I'm positive. Maybe at the end of the year we're here. Type of thing. So oftentimes that's why, spending money should be opposite to making money. So we want to say that area is signed. Okay, on to something a teeny bit more current. The fundamental theorem of calculus. So, fundamental theorem of calculus. Part 1. Okay, so again, I think some of this will be just repeating, what's already been said, but hopefully you'll get something a little different out of this. Okay, so what part 1 tells us is that if we have a continuous function g of t, so g of t needs to be continuous on an interval AB. Okay, so if we've got some continuous function, then basically I could say here's A, here's B, there's an X somewhere in between, and here's my function G. So since G is continuous on AB, I can draw the line from there to there, and I could pick my point X, and I could just say how much signed area is there between A and X. In this case, I made it all positive, so I could just say how much area is there between A and X. And I could say that's a function. So there's some function, I'm going to say f of x, which equals this area. So I might as well invent some symbol and say what do I mean when I say this area here? Well, that area is given the symbol saying I take the area from A to X, G of t, and then I put a dt on the end. So this is just a symbol saying I take this area and I give it a name. So this is just a symbol. It's defined based on areas. What the fundamental theorem of calculus tells us is that then, if I do this and I define this function based on the area, well, then I could take the derivative of that function, f prime of x, and what the fundamental theorem of calculus is really telling me is, given all this situation where I've set this up and I'm given something, then, well, if I wanted to take the derivative of that f, it would be just plugging in the x for the t. So it's basically saying that this thing that we said was some function where you take the area, we can give that a name, and we can call it the antiderivative. Because if we take the derivative of it, we get the thing back. So we anti-derived it. We did the opposite. Okay, that's part one. And when would we sort of use it? So part one is used when we say know that we have some continuous function, and we want to say that there exists some antiderivative. I think the most prototypical case is that Newton gave us that F equals ma, where a is the acceleration. Well, I know acceleration is my function, or my forces. You have to be continuous. M is just a number, so a is going to be a continuous thing. So I could say that a of time equals F, the force at a particular point in time, divided by the mass. Okay, so now I've got a continuous function, a of t. I want to say that I can define a concept which captures, if I accelerate it, then at what point is it, how much is it moved? So, or how much speed has it gained? Sorry. So I can then just define that as some function. Here's my forces. I divided this function by m. I get some function a. I then can say, oh, well, there's some function. There exists some function. We'll usually call it v, equal to the antiderivative. Here we'll say from 0 to x. Oops, sorry. V of x, a of t. Very important we keep all our variables straight. This x, that x, this has a t, d, t. So I know this function exists. I could play that again and say that, well, this is some continuous function, and then I know that then I get that the integral of that is going to, or the antiderivative of velocity gives me position. So I could figure out the position by knowing the acceleration, by knowing the forces. So if I know the forces and I know they're continuous, I know it's got a position function, and I can solve for that using antiderivatives. Check. Part 2. So this is really sort of something kind of opposite. This is the idea that if I have a function f of t, and I'm integrating it from some a to some b dt. So I want to know this, essentially the area, and I know that for some function, big F of x, that equals, that its derivative. So I have some function, I don't know what it is, but its derivative equals f of x. So t x, but same function. So this is just using the variable x because this has an x. So I know there's some function that if I take its derivative, I get f of x. And I want to know how much area is under f of x from a to b. Well, then the fundamental theorem of calculus, part 2, tells me that this equals, we take the big F, we plug in a B, minus big F, and we plug in an A. So how and where is this useful? So what this is sort of really telling us is that, like, you know, if we have, say, a little car, so here's our little car, and it's going to, say, drive from time 0 to time, say, 10 minutes at, let's say, 60 miles per hour. Oops, losing me off the edge here. Perfect. Okay, so I've got a car, and it's going to drive from time 0 to time t at exactly 60 miles an hour. We won't worry about the fact that a car can't start going 60 miles an hour. It's already going that fast. Okay, and I want to know, how far does it go? Well, I can say that it's got 60 miles in an hour, and it goes 1/6 of an hour, so it goes 1/6 of those 60 miles, so it goes 10 miles. So really here, in some ways, I'm using the fundamental theorem of calculus in the fact that it says that this is just a constant function. Here my little f of x is just 60, the constant. Oops, sorry, 60 hours. Oops, and then I did this in minutes. In order to convert from minutes to hours, I should do this as 1/6. So it's 0 hours to 1/6 hours at 60 miles an hour. So I had the function 60 from 0 to 1/6, and I calculated its area, and I got 10. Okay, so on the other hand, I know that the antiderivative of 60, if f of x is 60, I can have a function whose derivative is 60, namely big F of x equals 60x. If I took this function and I take its derivative, then I get 60, my f of x. Okay, so that means that then I could take 60x and plug in 1/6, and I get 10, minus 60x, plugging in 0, and I get 0, equals 10. So we get the same area. But notice here, I didn't have to say at all that, was the car starting in Denver or was it starting in New York City? Maybe I don't even actually have to use this f of x. This f of x could be that the car was, you know, actually starting at 100 miles an hour and it went 60 miles an hour faster. So, sorry, that's a bad analogy. This is position. So it's kind of like if the car starts in Denver, or does it start 100 miles away from Denver? If it travels at 60 miles an hour and all I care about is how far it goes, then I don't need to know where it starts. Where it starts is going to be this constant. And that essentially will just go away when I take this derivative. Or you can notice that you get the constant minus, and then that same constant's going to pull up here, and it'll just cancel, always. So any kind of constants go away. That relates to the real world situation of basically we don't care about starting if we only care about the area. It could be the area here, or it could be the area over here. Wouldn't matter. Okay, I hope that helps. Just to review a teeny bit, you use the first part of the fundamental theorem when you have a continuous function and you want to say that its antiderivative exists. Also, that means that then if I have a function that is defined as its antiderivative and I take the derivative, I have to basically get back the original function. Okay, second part says if I have some function such that its derivative is the function inside, then I can figure out the area by plugging in the endpoints into the antiderivative function. So I don't want to call this an antiderivative because antiderivative is really what we defined here, but the derivative of big F is little f. That's what I know. Then it tells me, how do I calculate this definite integral? By plugging in the endpoints and subtracting. All right, hope that helps.